Hello everyone, welcome to the TOMILO interview room. I'm your host, Yun Yun. Today, we are honored to have invited an expert in the field of new energy vehicle electric drive testing, Senior Solution Director, Mr. Zhu, to provide in-depth answers regarding electric drive reliability and environmental testing. Hello, Mr. Zhu.
Hello.
Why did we choose this topic for sharing in this episode?
As we all know, new energy vehicles primarily consist of three major systems: the battery, motor, and electronic control systems. In previous episodes, we mainly discussed the battery module of new energy vehicles, explaining the reliability testing of power batteries. In the entire testing system for new energy vehicles, the electric drive system as one of the key systems is equally critical in terms of reliability.
That's absolutely true. I noticed the term new energy vehicle electric drive system mentioned in the topic. What exactly does this system include?
The electric drive system of a new energy vehicle refers to the electric drive assembly system, abbreviated as EDS. The drive assembly is the core system for the vehicle's power output. It includes three major components: the drive motor, transmission, and motor controller. The motor, as the core component of the power output in new energy vehicles, mainly falls into two categories. The first is the three-phase asynchronous motor, and the second is the permanent magnet synchronous motor. These two types are widely used. Three-phase asynchronous motors have mature technology and stable products. Permanent magnet synchronous motors with their embedded permanent magnets in the rotor. However, permanent magnets may experience permanent demagnetization under high-temperature environments. In extreme usage scenarios, this could lead to permanent performance degradation of the motor, offer higher output efficiency compared to three-phase asynchronous motors. The controller is responsible for converting the direct current from the power battery into alternating current, driving the motor to output mechanical energy. The transmission is a mechanism used to change the motor's speed and torque. It can fixedly or stepwise change the transmission ratio between the output and input shafts. Therefore, the technical level and reliability of the electric drive system directly determine the driving performance and overall reliability of electric vehicles, making it one of the most critical subsystems in new energy vehicles.
The electric drive system is indeed very important. So, what types of tests do we need to conduct to ensure the safety and reliability of the electric drive system, and what do these tests entail?
Let's start with the integrated EDS assembly and then break it down layer by layer. For the assembly, we primarily conduct endurance tests, performance tests, and NVH tests. In terms of endurance, at the assembly level, we focus more on mechanical durability, including housing fatigue. Similarly, for the motor, performance testing mainly involves the mapping and measurement of the motor's efficiency map. The third module also includes NVH testing. For the motor, endurance testing revolves around materials, deformation, insulation aging, motor winding solder joints, and insulation layer aging, among other failure mechanisms. The third module corresponds to the transmission, which also undergoes endurance tests, tilt tests, to check whether the transmission operates effectively in different postures, and NVH tests. For transmission endurance tests, we focus on different types, such as longitudinal transmissions, transverse transmissions, parallel axis transmissions, and coaxial transmissions, testing aspects like lubricant viscosity, seal aging, and gear solder joints. Lastly, there's the motor controller, which mainly undergoes endurance tests.
So, there are four types of tests: endurance testing, performance testing, tilt testing, and NVH testing. In these tests, are there any technical challenges that our customers are particularly concerned about? Does TOMILO have any unique solutions to address these challenges?
Generally speaking, for reliability testing of the electric drive system, we don't typically install it in a vehicle and run it for 15 years or 300,000 kilometers. Instead, we use the Kaufman-Manson model for accelerated aging to shorten the component testing cycle and verify the aging of the system and components under thermomechanical stress. The detailed test cycle curve is shown in the figure. This graph represents the PEC curve often encountered in electric drive system testing, which stands for Power Temperature Cycle Endurance Test. The standard is IEC 6006214, the temperature cycling curve, to ensure the effectiveness of temperature cycling in accelerating aging. The sample must maintain stable linear fallibility during cooling, especially below -30 degrees Celsius. Our company uses independently developed intelligent control systems with segmented and variable gain control based on the different characteristics of dynamic operating conditions. We ensure stable linear fallibility across different temperature ranges from multiple dimensions. Of course, in addition to good performance through segmented and refined control strategies, the system also demonstrates excellent energy efficiency. The energy consumption during the entire testing process is 30% lower than with traditional control strategies.
So, to ensure the sustained high performance of new energy vehicle electric drives, what other conventional tests are there and what challenges are often encountered during testing?
Since the electric drive system laboratory involves a wide variety of equipment, the requirements for the structural layout and interface design of the environmental chambers are very high. It requires a deep understanding of the customer's laboratory design planning, actual testing processes, and electric drive components to provide the best matched solution. Currently, the most common testing pain points in electric drive laboratories mainly include two aspects. First, the wide variety of electric drive samples makes assembly and disassembly complex, with limited space for loading and unloading operations. Second, the numerous openings for water, electricity, oil, and bottom support fixtures pose high risks of air and cooling leakage.
Taking passenger car motor samples as an example, how is the unit structure designed? From what I understand, the loading and unloading space for motors is very limited. Regarding these 2 points, does TOMILO have any specific solutions?
As mentioned earlier, electric drive laboratories involve many types of equipment, such as iron floors, dynamometers, battery simulators, PDU cabinets, frequency converters, control systems, environmental chambers, water chillers, oil coolers, etc. The entire laboratory space is very compact. The connection relationship between the sample and the dynamometer. For a single motor test, one dynamometer is required. The motor is connected to the dynamometer at its end face. For assembly testing, 2 dynamometers are required. The assembly sample is connected to the 2 dynamometers via a connecting shaft. For transmission testing, 3 dynamometers are needed. One shaft directly connected to the input dynamometer, and the other 2 shafts connected to the output dynamometers. Our environmental chambers can provide customized product solutions based on the position of the dynamometer and the available space on site. For example, we offer integrated layouts, split-type remote layouts, and one-to-many layouts, making full use of the on-site space for flexible arrangements, and providing effective loading and unloading space for samples.
So, there are many testing scenarios for electric drive test benches. For the issue of opening insulation in different laboratory scenarios, what unique solutions do we have?
For the drive and output shafts, we use high and low temperature resistant felt and brush seals. The soft brush can directly contact the thin shaft, ensuring sealing and insulation effects. Compared to brushes, felt offers better adaptability to different aperture sizes. When the shaft diameter varies significantly, felt seals can be used by creating corresponding holes in the felt, or using a cross-shaped opening for the shaft to achieve sealing. For the bottom pillar openings, standardized elastic ring-shaped silicone plugs are typically used for sealing, ensuring both sealing effects and providing some vibration damping.
Different laboratories indeed have varying requirements. So, based on these different requirements, what kind of valuable solutions can TOMILO bring to customers?
TOMILO, with a deep understanding of customer laboratory construction and application testing scenarios, highly adapts to the needs of various bench suppliers and end users, providing precise and efficient testing solutions. First, comprehensive design interface sealing solutions can meet the complex requirements of multiple mechanical interfaces. Second, flexible structural design achieves excellent spatial performance, making it convenient for customers to use. Third, the independently developed intelligent control system ensures stable product performance under different testing conditions. Through these systematic designs, we ensure more efficient and stable performance for the electric drive system, safeguarding its reliability.
Regarding electric drive test benches, the main concerns for the public are whether the bench performance is stable, whether assembly is convenient, and whether the sealing is reliable. Correspondingly, today we introduced the commonly used temperature cycling endurance tests, motor assembly processes, and TOMILO's complete and advanced testing solutions. Thank you, Mr. Zhu, for the detailed explanations. We hope today's discussion has provided everyone with a deeper understanding of electric drive bench reliability. We'll see you in the next interview. Goodbye.
Goodbye.